Welcome everyone once again to Zahid's data mining channel. My name is Zahid Islam and I work in the School of Computing and Mathematics, Charles Sturt University, and this is my URL. You can learn more about me from this URL, and this is my email address. You can email me if you have any questions. Today I will be talking about a technique called SIMI, which is a missing value imputation technique, and we published this paper in Knowledge Based Systems in 2013, and the paper is available online. So what is missing value imputation? When we collect data sets, for example, this is a toy data set, an example of a toy data set, then there will be some values missing always. That's generally the case, right? So when you collect a data set, then you will see that some values will be missing for various reasons. For example, survey questions were not answered, your sensor did not work as you expected for various reasons, for mechanical faults, for battery flat battery, and so on. So you will have some missing values. Then there are techniques that to impute the values. A very primitive technique is mean imputation. For example, if you know the salary of the whole cohort or whole population, you can calculate the mean, and well, you can estimate that that is the mean salary of that. But again, the techniques, that type of approach is not very sophisticated. So people always try to come up with better imputation techniques so that they can make the educated guess better and more accurate. For example, in this case, we are imputing the value of the missing data, and then we impute it to be 85.2, whereas the original value is 85. In this case, we have an original data set, and when we build a new or develop a new model, we generally have an original data set with no missing value, and then we artificially create some missing value and apply our technique to impute those missing values, and then see whether our technique can actually impute the values accurately or not. Because we have the ground truth, we can compare. We have the original value 85, and then we artificially consider that it is missing, and then we have an imputed value. We can cross-reference, we can cross-check whether the value is correct or not. This is all. This is what we call it as missing value imputation techniques. Missing value imputation or making educated guess is useful generally. For example, we have seen in our small experimentation that if we build a classifier from a data set like this where the missing values are imputed, then the classifier is generally more accurate than the classifier that we can build from a data set like this where there are a lot of missing values. And we compared one of our technique with some existing techniques, and we saw that our accuracy is better. So it tells us that missing value imputation is useful. Now there is an existing approach, missing value imputation technique called EMI by Schneider et al. In 2001, proposed in 2001, where a missing record, R is a record and RM is the value of that record that is missing. Okay, so if we have a record with some missing value, then it is calculated as the mean of those values. Right, so the missing attribute, so M, say for example M is an attribute, then M has a missing value. So what is the mean of M? So that is the primary contributor to the imputation, plus this part where A is available, that same record R, but say for example A is an available attribute, the value of which is known. So it calculates what is the value of that and how much it deviates from that A attribute's mean. So if it deviates heavily from the mean, and Q is the correlation between A and M. Okay, M is the missing attribute, A is the available attribute, Q is a correlation kind of thing between A and M. So if the idea is, if the R records, the record R has a huge deviation in attribute A from its mean value, from the mean value of A and the attributes are correlated, then the value for M will also similarly deviate from the mean value of M, something like that, right? And if the correlation is weak, then it doesn't matter. For example, the correlation is 0, then we cannot actually, although we know that our record R's, A attributes value has deviated heavily or not deviated heavily, but that does not give us any clue whether the M attributes value will also deviate or not, because there is no such correlation between attribute A and attribute M, something like that. So now actually in this case Rm is a vector of missing attributes. It doesn't need to be only one attribute. If there are more than one attributes, then mu M is again the vector of the mean of those attributes, and so on. So we can use that. So this was the EMI technique's basic concept. So we studied that and we realized that there are two things. One is, if the correlation of the attributes are high, then actually it will be more useful. If the correlation between the attributes are not high, then this technique will be more or less same as the mean imputation, the early days technique like mean imputation. So we will have no other clue other than considering that, okay, whatever the mean of this attribute, consider that as the imputed value. Now we cannot increase the correlation of a data set, correlation between attributes of a data set, because we cannot change data set, right? So then we thought that what we can do is we can actually find out the horizontal segment of the data set, a suitable horizontal segment where the correlation among the attributes, correlations among the attributes are high. I will give you an example. Say for example, if we consider the whole population of a town, say Sydney, and we consider, okay, what is the correlation between age and height of the population in Sydney, and maybe we will find out that there is no relation. Maybe somebody is older but shorter, somebody is younger but taller, whereas another person older and taller and another person younger and shorter. So there will be no such correlation between age and height. But if we find out a horizontal segment of the population of Sydney where everybody is between the age 0 and 15, then we will see there is a much better correlation between age and height. So although we cannot change the whole data set and we cannot change the correlations among the attributes of a data set, but what we can do, we can find out suitable horizontal segments, and then within those segments we will find higher correlation between the attributes, right? So if we can do that successfully, and then we impute a missing value of a record considering other records within the same segment, then we are likely to get better imputation. That is the basic concept of this technique, right? And what we did in that case, how do we find better segments? So we actually build decision trees. Okay, so this is, for example, the whole data set, and there are, say for example, 15 records. R15 is the 15th record. We can build a decision tree to classify a class attribute, and then we say, for example, our first tree TX has 3 different leaves where R1, R2, R3, R4 and R5 belongs to leaf 1, and other records are divided into other leaves. So that can be pictorially demonstrated like this. So this tree has 3 leaves and these are the leaves. So this is possibly leaf 1, R1 is in leaf 1, and this is leaf 2, and this is leaf 3. So the whole data set can be actually divided into 3 leaves. And then we found that if we do that, then actually the similarity between the records go up. So if we consider the similarity between the records, average similarity between the records among the all records, R1, R2, R1, R3, R1, R4, R5 and so on, all possible similarities, and then we average out. So that similarity is not as high as the similarity within the segments among the records. Similarity among the records goes higher. if we divide them into groups. And then if we build another tree, say for example ty for another class attribute, or it's a forest algorithm, then we get another tree, and then we have another type of division or grouping of records. So this grouping comes from tree 2, and then if we overlap, if we intersect the leaves, if we overlap these two groupings, say we get this grouping, then we even get finer groups of records. Say for example, before all these 5 records were grouped together, but now out of those 5 records, these 3 are subgrouped and these 2 are subgrouped. So we get even finer groups. Now we can see that if we build even just 2 trees and intersect them, the similarity among the records within these small intersections are actually even higher than just one single similarity. And not only that, we then also found that the correlation among the attributes also go higher within these intersections, right? So for example, if we build 2 trees and then we got these 49 intersections, and we found that the correlation were higher out of 15 possible correlations, 13 of them were higher in intersection 1, 12 in intersection 3, and so on. Other intersections may not have. There will be some intersections that do not have any record. So this tells us that if we actually build a decision forest, a number of trees, and then get the intersections, we get very pure intersections where the similarity among the records is high and correlation among the attributes of those records are also very high. And then if you come back to this equation, you can see that equation will be more useful in situation like that. So that is the basic concept of this algorithm, and this algorithm uses a few things. For example, it first finds the trees and then it intersects, and in this case, this is just an example. There is one record in one intersection, so this record needs to be merged with some other intersection, or you can say these 2 intersections need to be merged. So there is a merging process, okay, in this algorithm. So why we need to merge? Because if the intersection size is very small, then there will be not enough significant correlation, or similarity will not be statistically significant. You cannot just rely on 2 records to impute another record. So there is a merging process. So if the merging process says that if the number of records of an intersection goes below a particular threshold, then we need to merge that intersection with another intersection. And while merging, we consider 2 things. So that 2 things. First, we merge in a way so that the similarity of the merged intersection is the maximum possible similarity, and the internal correlation of the attributes also are the maximum possible correlations of among those attributes after merging. So we merge very carefully. And then we also have seen that we have done some experiments, analysis to see how what is the result and how the results influence, etc. For example, we have seen that if the number of record in each intersection is 25, at least 25, then possibly that gives us a good result. In terms of RMSE is a metric for how accurate the imputation is. So in terms of getting good imputation, you need, if you have only 1 record, 5 records in a group, you don't get good RMSE value. We did that experiment on 2 data sets just to see that yes, our understanding is correct. We need a minimum number of record in an intersection, so we consider 30 is statistically considered useful, and we used 30 there. And then we did some experiment, but we also did some other experiment. For example, number of decision trees, how many trees we build, and we analyzed that based on a couple of datasets, CA datasets and CMC datasets. These datasets are all publicly available from the UCI machine learning repository, and we saw that when the number of trees increased, our imputation accuracy increases. RMSE lower means better, so our imputation accuracy increases, although the computational complexity also increases, and the execution time also and number of intersections also increase. But well, then if you increase number of trees, you possibly get better imputation accuracy. So it may be a 6 and 7 kind of number of tree is a good set of trees. Then we, as usual, we experimented our technique with other techniques, compared it with other techniques, and we found good results. Thanks for watching. Please feel free to download the paper and read it.